All right, let's wrap up the one sample t-test by looking at it with hypothesis testing. So here we go. We have our general question. Do students rate the dorms differently than neutral? So we take our more technical research question. Is the average student rating significantly different from a presumed average rating of 4 from all students, right? We see student rating is our sample. We're comparing it to the presumed population of all students, the presumed average rating of 4. So here are our same 7 steps. Remember, these are the same 7 steps you learned from the chi-square section. The only thing that changes is how we do our hypotheses and how we do our calculation and how we find our crit score. Everything else is the same. It's the same 7 steps, generally speaking here. All right. So again, that you can, if you remember them from the chi-square, then it shouldn't be that hard to remember the process for the t-test, especially the one sample t-test. Now, remember, we have our variables here. That's our first step. So our variable, our x variable is student rating, and we measured it on a scale of 1 to 7, continuous scale, so continuous data. Now, how do we do our hypotheses? Now, with t-test, the hypotheses can be non-directional or directional. So I'm going to show you the versions of each of them. Now, remember, you determine directionality from the question. If the question is directional, your hypothesis is directional. If the question is non-directional, the hypotheses are non-directional. So let me show you the non-directional or the two-tailed version of the hypotheses. I remember two-tailed is a version of the test you would use that goes with non-directional hypotheses. So, okay. So here we start with the alternative. If the question asks, is there an average student rating significantly different from presumed average rating of 4? Notice how the question is just asking, are the two averages different? It's not specifying any more than that. It's just asking, are they different from each other? So the question is non-directional. So the alternative says yes to the question. There is a significant difference between the average, keyword, got to include that because we're talking about means, student rating, there's the sample, right? The sample and the x variable, and a presumed average rating of 4. There's that as presumed population mean. So the alternative hypothesis is essentially saying that the sample mean will not be equal to the population mean. And the null hypothesis just says it's the same sentence, copy paste, you just put no. There is no significant difference between the sample mean and population mean, right? So the null is essentially saying that the sample mean is going to pretty much be equal to the population mean. So this is how you would write the hypotheses if your question was non-directional. Now, what if the question was directional? Here's how you would phrase it. Let's say the question said this: is the average student rating significantly higher than a presumed average rating of 4? Or it could say, is it significantly lower, right? It's not going to say both of them like I showed you here. I wanted to show you both options. It would say one or the other. So if it specifies the difference, is one higher than the other, for example, then the question is directional. You would need to use a one-tailed test, and your hypotheses would be directional as well. So the alternative is going to be phrased like this. If the question asks, is the student rating significantly higher than, then the alternative says yes to the question. The average student rating is significantly higher than the presumed average rating of 4, right? So the alternative in this case would be saying that the sample mean is greater than the population mean. And remember, the null with the directional hypothesis, the null hypothesis is going to specify the 2 ways that the alternative is not true. So the sample mean cannot be higher than the population mean if the average student rating is significantly lower than or equal to the presumed average rating of 4. So the null is saying that the sample mean can't be greater than the population mean if the sample mean is actually less than or equal to the population mean. Okay, so you can copy the same sentence. You just got to specify the other direction. If the alternative said higher, the null says lower. And then that second part equal to, right? Because remember, it has to be the other direction, but also they could be equal. One can't be higher or lower than the other number if they are equal to each other. Now, if the question were to say, is the sample mean significantly lower than the population mean, the alternative would still say yes to the question, and it would say, yes, the average student rating is significantly lower than the presumed average. So it's all based on the question. Whatever the question says, the alternative says yes to, and the null says no to the alternative. So if the question says higher, alternative says higher, null says lower, equal to. If the question says lower, the alternative says lower, and then the null says higher or equal to. So the directional hypotheses have a little bit more specificity, a little bit more detail to them, and they can be a little trickier to write. So that's why just refer back to these hypothesis slides to when you're trying to write your own hypotheses yourself. Follow this template here because that's how you're expected to write them. All right, so let's start to put this together and do our hypothesis testing. So remember, here's our scenario. 100 students take the questionnaire. We want to know, is the average student rating different from 4? Here's our variable, student ratings. Shorten the hypotheses for the sake of space. Remember, you got to write them out. Essentially, the alternative says the sample mean will be different from a population mean of 4. The null says that they will be pretty much equal. Now we got to calculate our t-score. So remember, our t-score that we calculated is 2.629. Okay. And now what we need to determine is how likely were we to find this difference between the average student rating and a presumed rating of 4. If we assume the null is true, if we assume the average student rating should be equal to the presumed rating of 4, how likely were we to find this difference that we did find? Okay. So remember, we have to find the probability, because if the probability of our t-score is less than 0.05, then finding that difference we found between our sample and population means is considered unlikely. Now, just like we did with the chi-square, the software you use for your assessments will calculate an exact probability for you. But you also need to know how to do the workaround. Remember, the workaround is using what's called a critical score. So just like we had chi-square critical scores, we have t-critical scores, or t-crits. And you're going to find them using the t-distribution, or the t-critical table on that critical scores PDF. So go ahead and get that in front of you and locate the table that says t-critical scores table, something to that effect. Now, if the t-score goes past the t-crit, then it has a probability less than 0.05. If it's before the t-crit, it has a probability greater than 0.05. So the comparison here with t and t-crit is just like with chi-square and chi-square crit. The comparison is exactly the same, and it's going to be the same for all statistics that you're going to learn. It's just the calculation and the critical score that we use is different, but the comparison is the same logic. So here's how we have to use the t-table. And I'm going to walk you through this because there's 2 different versions of the t-crit that you can find depending on if you're using a 2-tailed or a 1-tailed test. Okay. Now, if the hypotheses that you're using are 2-tailed, because the question you have is 2-tailed, then you have to look on the 2-tailed side of the table. If the hypotheses are 1-tailed, then you have to look on the 1-tailed side of the table. And then in a 1-sample t-test, you use your degrees of freedom to find the row, just like on that chi-square critical table. So degrees of freedom is n, your sample size, minus 1. Okay, so you take the total sample size minus 1. Now, let's do some practice with that. What is a t-crit when alpha equals 0.05 if you have a 2-tailed test and n equals 8? Okay. Now the critical, so what the critical score you should find, you look at the 2-tailed side, so the right side of the table, look at the 0.05 column, n is 8, so 8 minus 1 gives us 7 degrees of freedom, and we see that 2.365 is the intersection of the column and the row, and that's our critical score. Now, what is the t-crit when alpha is equals 0.05 and we have a 1-tailed test and n equals 12? Well, look on the 1-tailed test side, that's the left side of the table, and we know that the column is 0.05, 12 minus 1 gets us a degrees of freedom of 11, and that is 1.796, and that is our critical score there, okay? So that's how we will find that critical score. Now, a few last details about finding the critical scores were in regards to 2 versus 1-tailed test, okay? Now, if it's a 2-tailed test, so say that we have a t-crit of 2.365, well, that t-crit goes on both tails. If you're looking at like the distribution of data, we're going to mark off the upper tail and the lower tail, right? So if it's 2-tailed, the t-crit goes on both tails. So when we put our t-score, we need to see, does it go past either of the t-crits or is it before the t-crits? So we know that positive 2.450 goes past positive t-crit 2.365. If it was negative 2.450, it would be past the negative version of the t-crit on the other side. Okay, so it goes past it. So because the t goes past the t-crit, we know the t-score has a probability less than 0.05. It's significant, so we would reject the null. Now, what about when you're dealing with a one-tailed test? Well, because it's one-tailed, that should indicate to you that it's going to go on one of the tails, just one, not both of them, because it's a one-tailed test. You're only looking at one side of the distribution. So t-crit of positive 1.796, that's the one you get from the table. Now, the table is not going to show you if it's positive or negative. It's just going to show you the positive. So how do you know if the t-crit goes on the positive tail or the negative tail? You have to look back at your alternative hypothesis to determine this. If the alternative hypothesis is saying specifies greater than or higher than, you would put the crit on the positive side. If the alternative says specifies lower than or less than, then you would put it on the negative tail. The reason for that is if you have a sample mean that the alternative says the sample mean is greater than the population mean, then when you take the difference between them, you get a positive result. If the alternative says the sample mean is lower than or less than the population mean, then if you take the difference would be negative, right? Because one is the sample mean smaller than the population mean. So that's why that's why the alternative determines which tail to look at. So let's say that our alternative says greater than, we would put this t-crit on the positive side, so 1.796, rounded there a little bit there, but always keep the t-crit exactly as it's phrased from the table, okay? Now, a t-score of 2.450, right, is that going to go past or before this t-crit? It's going to go past it, right? Now, notice if you put the t-crit on the wrong side, let's say you put it on the negative side, okay? If it was put on the negative side, so for example, then your result is actually before, and then it is not significant, and you would not reject the null. So that changes things there. So you want to make sure that you get your critical score exactly where it needs to be on a one-tailed test. All right, so let's continue on with our example here. So let's find our critical score table. Let's find our critical score for our scenario. Alpha is 0.05, two-tailed test, n equals 100. Now, a heads up, when you're looking at finding the critical score, when you're looking at the table, if the exact degrees of freedom you calculate is not on the table, the rule is to round down to the next lowest listed. So what I mean round down is if the t-score, if n is 99 and the table only lists 95 and 100, then you round down. You don't round up to 100. You round down to 95. The rule is to be conservative with your numbers. It's better to take some numbers off than to add numbers on that you don't have. Okay, so if it's not listed on the table, round down to the next lowest listed. Now, what you should get is a t-crit of 1.986. Now, because our hypotheses and our question are non-directional, that score is going to go on both tails. We remember our t-score is 2.628. And we see that that goes past the positive crit score of 1.986. Because it goes past, we determine that this has a probability of less than 0.05. Okay, it goes past the t-crit. It is statistically significant, meaning it was unlikely to find this, assuming there was no difference between our means. So we take that as evidence against the null hypothesis, and we decide to reject it and accept the alternative as our conclusion. And so we restate that hypothesis as our conclusion. There is a significant difference between the average student rating and a presumed average rating of 4. And then lastly, we need to take it together and put it as a general conclusion. So put it back in the language of the general question, and that would be students rate the dorms differently than neutral, either higher or lower than. This analysis didn't determine that. We just know from our situation that the students rate the dorms differently than neutral. And that is how you do the one sample t-test with hypothesis testing.